A video camera is focused on a rocket on a launching pad 2 miles from the camera. The angle of elevation from the ground to the rocket after x seconds is pi divided by 120 times x. Part A, write a function expressing the altitude h of x in miles of the rocket above the ground after x seconds. Ignore the curvature of the Earth. Okay, well, let's draw a picture of the situation. So we've got a rocket. Here's the rocket. And it took off from a launch pad. And we're presuming flat ground or close to it. And then 2 miles away, there's a camera down here maybe. 2 miles away. We're assuming the rocket's going straight up, so there's a straight angle there. And we're creating a right triangle. And we'd like to know the height. We'll call this side h for height. And we actually want the height in terms of x. Well, what's x? Well, x is actually involved with this angle here, and it's pi divided by 120 times x. Okay, so what are we given? We're given this length. This is our angle. And we want h. So this involves the TOA part of SOHCAHTOA because we want the opposite side. We have the adjacent side. So tangent equals opposite over adjacent. Oh, okay, so let's set that up. The tangent of the angle, which is pi over 120 times x, is equal to h over 2. Now, if I multiply both sides by 2, so go 2 times both sides, this will cancel, and that'll leave you with h by itself. I'm going to turn it around. I'm going to put h on the left side and say h is equal to 2 tangent pi divided by 120 times x. And if you change to function notation, you can say h of x. That means h of x. The input is x, the output is h. Function notation. And so that's part A. In part B, we're graphing that function. So we're graphing this guy. Okay, so I'm just going to graph the whole thing, and then I'll have to make some adjustments. So there's your xy plane. And whenever we graph the main period of a tangent function, we graph the asymptotes to the left of the y-axis and right of the y-axis, same distance. Away from the y-axis, just in the opposite direction. And I usually graph 3 points between the asymptotes. I plot the x value at 0, halfway between the y-axis and the asymptote, and on the right, and then also on the left. And I don't know what these values are yet. I'll find them in a minute, but the way the graph looks never changes. So it's going to look, it's going to have a point here, a point here, a point here, and as you go to the right, it will approach its asymptote on the right, and as you go to the left, it'll approach the asymptote going down. As you go to the right, it goes up, and it never actually gets to the asymptote. It goes up infinitely high before it gets to the asymptote, and it goes down infinitely low on the left before it gets to the left-hand asymptote. And then I noticed something, that we're only supposed to graph it from 0 to 60. That's interval notation. So x can go from 0 to 60. We could actually include 0. So it could be this interval. as well. But you're never actually going to get to 60, as you'll see, because the period of this thing, remember how we get the period, we take the normal period pi divided by this number. And so that's divided by pi over 120, but you divide by a fraction. That's the same as flipping and multiplying, so that's equal to pi times 120 over pi times 120 divided by pi. And you just get 120. So the period for this thing is 120, which means the distance between the asymptotes, that's the length of the period, is 120. Oh, okay. That means out to one asymptote is half that distance, because the y-axis, the x value of 0, which lies on the y-axis, that's right in between them. So so the equation of this asymptote has to be half of that 120, which is 60. And then I don't even need the left-hand part of this graph. So I can erase all of that, really. And then this number here would have to be half of 60, which is 30. And then what does it go up to? Well, this number is always going to be the number out in front, height-wise, so that's going to be 2, and that's going to be negative 2. How do I know that? Well, if you plug 30 in here, you get, well, you get pi force, and the tangent of pi force is 1 times 2 is 2. So that's the graph that we want for part B. And then in part C, you're asked to evaluate and interpret the values of h of 0 and h of 30. h of 0, well, that's just 2 times the tangent, pi over 120 times 0, but that's the same as the tangent of 0. And you can see from the graph that the output's going to be just 0. Oh, so it says interpret that value. Oh, it's just the rocket's still on the launch pad because the input is in seconds. That's 0 seconds. So that's right as the rocket's about to launch. So the rocket hasn't launched yet. It's sitting on the launch pad. And then h of 30, if you plug in 30, oh, well, that's the value we plugged in to get the height at that point. So h of 30, that's going to be 2. Remember what h is in. H is in miles. So that means after 30 seconds, the rocket is 2 miles above the Earth. So the rocket is 2 miles high. And then in the last part, part D, what happens to the values of h of x as x approaches 60 seconds? Well, x equals 60 is the vertical asymptote. What happens graphically is as x gets closer and closer to 60, this graph is going to shoot upwards. And it's the closer you get to the asymptote, the closer x gets to the asymptote, the closer the height of the graph gets, well, the larger the height of the graph gets. So eventually this model breaks down. It's not going to make any sense because the height of the graph goes to infinity as x goes to 60. And anyway, long before that, it would be out of camera view. So the rocket gets higher as x approaches 60. And would eventually be too high to track. and the model breaks down because the rocket doesn't get infinitely high.